Robert, I've had a few piers over the years, not been entirely happy with any of them. Basically, I'd like a few straight answers.
Okay, I will if I can.
Well, it's quite well known that you don't like talking about your equipment or your designs. Why start now?
Okay, I mean, in all fairness, I love talking about the equipment, I love talking about astronomy. I probably don't like giving information that's going to help our rivals. It's a fine line between making more information available so that the customer can understand what's going on and explaining what I consider to be a considerable amount of research that we've done in development of our anti-vibration piers, and just parceling that up, putting a ribbon on it and passing it straight on to our competitors. I think we've reached a stage though, there's been so little discussion, open discussion on the internet and in popular literature about piers, that it's allowed a massive amount of misinformation, and we're seeing that misinformation now become fossilized in poor design, and there really is a lot of it around, and the wrong designs are being copied. I'm not doing this to help people copy our designs. I'm not really interested in the DIY market, you know. I've got to be honest about it and say I'm not interested in helping somebody make their own pier. What I am interested in doing is making it clear that good observatory pier design is an area of excellence. It's not something that's just knocked up by a blacksmith. It's in its way, it's a sophisticated machine, and it's as sophisticated as a telescope. I really don't understand people spending a great deal of their hard-earned money on a telescope and then plonking the thing on top of a bit of gas pipe and expecting it to get excellent performance out of it. The idea doesn't make any sense to me.
Can you show me what's wrong?
I think I can, yeah, absolutely. If you need to follow us out into the warehouse, and we'll take a look.
Okay, this is a type of pier that has spread like a virus over the internet. In fact, we're going to show you some pictures here of how common this design is, where people have sort of invented it themselves. They've taken a few ideas that they've seen on other people's websites, and this is typically the kind of design they're going to give their local blacksmith to cobble up from. At Astro Engineering, we call this generic type of pier the optimistic pier.
Optimistic? Right.
Okay, it's the optimism really is there's almost as much hope in this pier as there is steel, because there's a lot wrong with it. Let's start really with the base. Now the base looks okay, it's fairly substantial at about 10 mil, but it's way too short. It hasn't got enough base width. So we're talking about far too small a footprint for any chance of this base plate to have the authority to actually control the pier. So the base plate's the first problem, regardless of what actually moves on top of it. Also notice here that the makers have put a long slot in the base where the fastenings actually go to hold it down onto the concrete base. Now they've done this because they imagine this improves the performance of the pier in terms of getting north-south alignment. Now, in all fairness, it's a disastrous idea. They have hugely weakened the performance of this base plate, which was poor to start with. And what they've done by adding this slotted hole is greatly impede the rigidity of the base plate. So this is just a plain bad idea, putting these slots in here. They basically impact on the performance of the pier for its entire lifetime and give you what? They shorten the setup of the pier by 10 minutes. So what? Take the extra 10 minutes when you're setting the pier up. You don't need slots at all. You'll never ever see a slotted hole in one of our piers, not while I'm alive. Okay, moving right up, we've got these fins that have been put on. They're miles too short. There is no way they're really doing anything useful in stabilising this pier. Probably if you took them off and you used a sensitive telescope to actually measure the difference with them being on and off, you probably would see a difference. But it's so tiny, it's not really making a useful cash contribution to the performance of the pier. And the reason for that is, one, the baseline of the fillet is too narrow, partly caused by the very small base that we've got on here. They simply don't come out far enough. And again, they lack the engineering authority to control this parallel pipe that's on top of it. Basically, they need to come all the way to the top here, and they need to be thicker, chunkier, and to have a much wider baseline if they're to make any useful contribution to stop this pier actually vibrating.
Whether it rings.
It does. In all fairness, it's not going to ring quite that much when it's bolted down, but it's still going to ring. Now, the main reason it's going to go into oscillatory vibration is this parallel pipe. We found in our tests that if you have more than about 5 inches of parallel pipe, it's going to flex. It's actually going to go into oscillatory vibration. That brings us up to the head here. Now, this is a contrivance that at Astro Engineering we somewhat uncharitably call the rat box.
Rat box.
Yeah, the rat box. We can't see any earthly reason to do this on the pier. It's a very common and copied idea. You see this on a lot of, tragically, on commercial piers, this has started turning up. It's a really bad idea. We think the only reason anyone would want this is to put a bit of chicken wire around it and put a small rodent in here to keep them company while they're out with the telescope. Because really, it has absolutely no useful function beyond that. Right. It's not easy to see really what's going on here unless you get to grips with the misunderstandings that the maker of this pier has actually got on their mind. The reason they've done this is to allow for the levelling of the pier head. Now, as I think you probably know, Ralph,
you don't have to level a pier head.
Absolutely not, that's right. The important thing, as I know you know, with aligning, getting polar alignment with a telescope mount, be it a German equatorial mount or maybe even an SCT, is one single alignment, and that's the right ascension axis through the mount pointing directly at the North Celestial Pole. That's it. That's all you have to do. How you achieve that, you don't need the head to be level. You don't need any part of the pier to be level. To compromise the pier in this way, by putting on a structure that you absolutely do not need, the fact that it may take you, if your pier is wildly out of level, it may take you a little longer to do your polar alignment. What do you care?
But once
you've got it done, it's done for the lifetime of the pier. I think if the rat box or levelling platform, if its main offence was purely redundancy, frankly, I don't think I'd have too much to say about it. It's not just a question of it being unnecessary. The rat box is positioned at a point on the pier that is absolutely crucial in terms of achieving and mediating the performance of the pier to the telescope that's mounted on top of it. To have this very rapid, sudden change of materials density, we've got the pier coming up. Even though we've said those other things about the pier, which were less than complimentary, we've got this really quite substantial structure, supported 360 degree, suddenly changing into mainly air, supported by these thin struts. And it doesn't really matter whether you've got 3, 4 or even 5 of these, you're still leaving the main perimeter of this platform unsupported. There's really nothing here stopping this going into rotational shear vibration, as well as simple flap of these sides here actually moving backwards and forwards. Anything that you've done here has been completely undermined by the rat box, and it really renders this, it's vastly worse than redundancy. It's actually imperiling the whole performance of the pier and almost guaranteeing you're not going to get sound performance out of the system as a whole. A lot of people don't realise this, that vibration at the imaging plane looks identical to poor seeing.
I've quite often wondered if it's motor noise that's getting through the system.
Yeah,
it's
exactly.
not being damped by the
mount.
mount.
The mount, of course, is a very dynamic structure, and it's often a very significant part of the overall installation weight. And of course, as the mount is moving with the telescope on it and the inertial moment is being challenged by the worm and the gear, typically on most amateur telescopes, the worm, or at least the motor powering it, is moving quite a bit faster than anything else on the telescope. And of course, that's setting up a source of vibration. And when you're down at the 1-2 arc second layer in the image, when you're recording images of that kind of resolution, you absolutely cannot tell the difference without using very sophisticated technologies like the DIM system, differential imaging technique, to spot the difference between seeing and vibration. And you'll find an awful lot of amateurs, and it's a very common thing, they'll with great alacrity tell you they're seeing. Oh, I never get better than 2 arc seconds, I never get better than 2.5, whatever it might be. What they never really question what they're reporting there. It's really the big difference between the professional and the amateur. Professional never makes that mistake. He always talks about what he can measure, and he leaves it open what might be causing it, because if you don't work with the idea that you've got good seeing, you will never harvest it. Eliminating vibrations is a great way of making sure that when your equipment is functioning properly and the sky obliges with good seeing, your equipment can then harvest it. The tragedy is with products like this,
you're really not going to get good imaging performance, because you're always going to think you've got bad seeing, because this thing is basically ringing like a bell most of the time for you. Okay, so let's take a closer look at the genuine article, the Astro Engineering Anti-Vibration Piers. There are a number of models. The ones we've got in front of us here, this is the AC282. It's almost a complete universal system. It's suitable for telescopes that mount from the top, like SCTs on wedges and that kind of thing, and also from underneath as well. So you can mount things like SCTs in Altaz mode, German equatorial mounts, you name it. The pier tops are completely universal. This is the 421. It doesn't feature the owl's nest like the 282. This is a solid all-round pier, and it's probably our classic anti-vibration pier. It's one we've been making for the longest time. It's truly universal. Again, there's lots of different types of heads. The most important thing, though, anything that mounts to this has to be mounted from the top down. There's no bottom up. Let's do exactly the same thing that we did before. Let's look at it from the ground up and ring the changes as we go of the difference between the genuine anti-vibration pier and the rest, basically. Obviously, the first thing to notice is the oversized base plate. It's a generous size. The base plate is, although it's very thick, it's a 10mm thick base plate, it isn't too thick. It's actually designed to distort slightly when the pier is actually bolted into position. We've got just one fastening hole against each web. There's actually 4 17mm fastening holes, but you notice they're round, they're not ob-round, and they're a generous distance away from the core of the pier. The next thing to notice are these full-length webs, which again are creating this conical shape for the pier. Now, the importance of these webs can't be overestimated. They're a very important part of the 5 different anti-vibration features the pier's got. This is one of the most important. And it's fairly simple to understand the role of the webs and their overarching importance in stabilizing the pier. Try to imagine taking a slice through the pier at this point and taking a simple point sample of the forces that are actually acting on the pier. Now take another slice through the pier, say at the top here. And if you try to picture in your mind the forces acting on the pier at this point and the pier at this point, something will be obvious to you. At this point, it's carrying this amount of the top part of the pier plus the mounting. Down here, it's carrying this plus the mount, plus it's carrying this amount of the pier as well. And obviously we've got this leverage effect of the increased length of the pier as it goes down. And that's where the oscillatory vibration is going to come in. Now, to null out the effects of oscillatory vibration, the holding forces, so the forces in the steel able to retain and resist bending, have got to increase as we go down the pier. Yeah. So in other words, we've got to have a conical shape. Now, these deep welds that are actually fusing the metal on at this point, if you took an X-ray of the pier, you would actually notice that they are severely distorted at this point. So these very deep fusion welds are actually grabbing hold of the steel at this point and puckering it. They're literally grabbing it and distorting it. So you would actually see distortions in the metal if you were able to X-ray. So all the way down here, we've got these distortions. Also, you'll notice the fusion welds in the base here as well, which are also being designed to do the same thing. So when this pier is bolted down onto the ground, this metal is actually designed to bend within its recovery range. So in other words, it's actually being challenged and the metal is actually flexing within its recovery range. You cut these welds off, the pier would have a chance to relax back to its natural position. But we're actually using the fact that welds distort metal is actually a problem a lot of the time. When you're making gas pipes and things like that, it can actually be a reason why the pipe fractures. We're actually exploiting it.
So what you've done in essence is to pre-stress the metal.
Yes, exactly right. Yeah. As we work our way up to the top, again, no sign of the rat box. Everything is solid.
Okay, one question. Where do I stick my rat?
I think you know where you stick your rat, to be honest, Rob.
A bite, Rob?
No, he won't bite. He's very tame.